it's really important, the normal distribution. It's really important because it's used to model hundreds of data sets in the world. When we take things like ACT scores or SAT scores, heights of and weights of young infants and babies and things like that, when they try to put people in certain percentiles for those things so that you can know where you're at. Okay, yeah, 68, 95, 99, 7 rule, Josie, we'll talk about that in a second. But when you want to take a set of data and you want to see, like, well, where are you at amongst the curve of people? Generally, the normal distribution is used because you can create a normal distribution based off of the mean of the data and the standard deviation. And then you sort of create a normal distribution, and you can calculate really easily with tons of different tools we have what the probability of being at a particular spot is. So like my kids particularly, my oldest, he was always in like the 99th percentile for head size. He has a really big head, and he's really skinny too. So he has a kind of a disproportionate body. But it was always, we would see that every time we take him to the doctor when he was younger. His height was this size, his weight was this percentile, and his head was always like 99th percentile. Means that his head was as big as 99% of other kids his age, and it strictly comes straight from that normal curve that we talk about in AP statistics. It has a symmetric unimodal shape, so putting together what you guys put over there in the chat. It follows the empirical rule, like Josie added just a minute ago. So basically what that means, if that's kind of new to you, you just need a little bit of brushing up. It means that 68% of all your data is within one standard deviation of the mean. 95% of your data is within two standard deviations of the mean. And 99.7%, which is essentially all of the data, is within three standard deviations of the mean. So I know last week, or no, 2 weeks ago in your cram pass, those of you who purchased a cram pass for AP statistics, you talked about how to check for outliers using IQR and Q1 and Q3. Another way that you technically can check for outliers is to see if it's outside of three standard deviations of the mean. And because, if it's in that 0.3% of the data, then it probably is an outlier. It's probably not matching the rest of the data set. It's way out there. Okay, since most of the data is within three standard deviations. I've seen a lot of AP rubrics on questions like that where they accepted that as an answer as well. For your upper fence and your lower fence, they accepted if you calculated it that way. So just a thought there. I think the more standard way of doing it is the Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. But when it's symmetric and you're using mean and standard deviation to describe the center and the spread, maybe the outlier would make better use of mean and standard deviation. Just a thought there to kind of connect those ideas from Unit 1. And just like any density curve, the area under the curve is exactly 1. Okay, so what we're going to be doing a lot of this afternoon is calculating the area under the curve, which is calculating what's also known as the tail probabilities. Okay, so this is an example here that is actually the empirical rule with IQ scores. The mean is 100, and you can see that they're actually a little bit more exact from this website. It came from spsstutorials.com. A lot of statisticians use that software, SPSS. You can kind of see it there in the watermark. They use that. It's like Excel, but a little bit more powerful, and you can create a ton of great models on that particular software. And they had this on their website. It was a good picture for us to look at. So the 68% is actually 68.2% if you want to be a little bit more precise. And you can see it's 95 is, I believe, 95.4%, or maybe I'm adding that wrong. I'm not really sure, but it's a little bit more exact. You can see instead of just 68, 95, and then 99.7, it's got a little bit more to it. Okay. But so your mean is 100. That's your center of your curve, center of your mountain, if you're thinking about it the way that Kate described it. And the standard deviation is 15. So we're adding 15, subtracting 15, add another 15, subtract another 15. That's how we get to 70 and 130, etc. Okay. Most of you are probably familiar with that. Now, what makes a normal curve the standard normal curve? What are the two things that are special about the standard normal curve? Y'all take a minute and put that into the chat. Standard deviation of 1 and mean of 0. Allison Henry. Awesome. Good job. That is exactly right. So when we have a mean that's, the curve is centered at 0 and it has a standard deviation of 1, that is the standard normal distribution or the standard normal curve. Okay. And these are used to calculate z-scores, which are very important because basically you can take a multiple set of data, something that's maybe about the ACT and something that's about the SAT, two scores, and you can standardize them to the same curve and see which one was better in comparison to the rest of everything. Okay, so if you have, someone's ACT score and the mean and the standard deviation for all ACT scores, and then you have their SAT score along with the mean SAT and the standard deviation of that data set, you could compare those two and see which test that particular student scored better on. I always say z-scores are a great way to compare apples to oranges. You're comparing ACT and SAT, which are graded on completely different scales. But if you standardize them to the same curve by calculating their z-score, then you can really see which one was actually better. Okay. And z-scores come up quite a bit on AP tests. This year, I don't know, with there not being calculators, they've made that pretty clear that calculators are not going to be necessary. However, they might be useful. They've always said it's not necessary, but they've pretty much implied that you really need one. So for this year, they've been a little bit more clear that calculators are not necessary due to equity issues of students not having calculators. But I think that you could have something like interpreting a z-score, which we'll talk about a little bit more later. So here's the standard normal curve. Okay. So if I am at 1, that means that I have a z-score of 1. Okay. Which we'll calculate, I think, some in just a second. So the z-score is at 1. That means that you are 1 standard deviation above the mean. That's what your z-score represents. How many standard deviations you are above or below the mean. So keep that in mind, because a positive z-score means you're in the upper percentile, the upper half of whatever group you're looking at. If you have a negative z-score, that means you're in the lower half, which, if you're talking about golf scores, you want to have a negative z-score. And if you're talking about, test scores, you generally want to be in the positive z-scores. All right. So like I said, a common form of standardizing statistics is to compare to from different populations is to use their z-scores, just like we talked about with SAT and ACT. This value is based off of where they would fall on the normal curve, where 0 is the mean and 1 is the standard deviation. The formula for a z-score is observed minus expected. So the observed is your actual score. And then your expected is the mean of that data set. So, if you're taking notes right now, you might want to kind of make that a little bit clearer. This is generally the vocab that's used in most textbooks and things like that. But you could say by observed, your actual score minus the mean score, and then divided by standard deviation. So if you're higher than the expected score, that's going to give you a positive z-score, right? If the observed number is larger than the mean. And here's our example. In Mr. of the Seven Isles AP Statistics class, the average grade is an 82 with a standard deviation of 4. In Mrs. of Arundel's AP Biology, the average grade is a 78 with a standard deviation of 2.5. Christoph has a grade of 78 in AP Statistics, while Sven has a grade of 76 in AP Bio. Christoph keeps claiming that he is smarter, since his grade is slightly higher than Sven's, right? 78, 76. Which student is actually performing better? I don't want to say smarter because, one of them's a reindeer, right? But yeah, so which one is actually performing better? How would we go about figuring that out? What do y'all think? You can feel free to post in the chat. Calculate each z-score. That's right. So if you have some paper and pencil or even just a calculator handy, y'all take a minute and do that. So we are going to calculate their z-scores, okay, for Christoph and Sven. So yeah, if you have a calculator handy, you should be able to do that with, just a calculator. I think that's how I did it when I was writing the slides. So feel free to chime in when you have Christoph's z-score and when you have Sven's z-score. Christoph's is -1. Oh, okay. I'll hold off. I didn't know if it was going to give you the work for both. So you can see the work there. I do believe Christoph's comes out to be -1. 78 minus 82. So his observed score was 78. His expected score was 82. That subtracts out to be -4 divided by 4 would be 1. And then we have one for Sven, -0.8. Can somebody else verify that with me real quick? We'll just use the thought that if multiple people get that. Okay, Olivia is in agreement there. Okay, that's -2, 76 minus 78 divided by 2.5, which does come out to be -0.8. Okay, so all of our math is in agreement there. All right, so which student is actually performing better in their respective class, Christoph or Sven? Sven, right? Because he is less below the mean, right? Christoph is a whole standard deviation below the mean for his class. Sven is not a whole standard deviation, okay? So since Sven has a higher z-score, he is actually performing better as a student comparison. Sounds to me like Christoph needs to let it go. We all need jokes, right? We all need these jokes. If you don't get this joke, then Google any of the names, and I'm sure you all get it. Anyways, okay, enough with my cheesy jokes. Maybe we'll save some more for later. We'll see. So kind of the next thing that comes up with the normal curve, and this may be the most common thing that we use for the normal curve because we use this skill when we are going into the inference section, is calculating probabilities using the normal curve. And I'm going to show you guys two ways of doing that, two ways of calculating the probabilities. There's one using the z-score table, which is not really fun, and most of you probably don't use that. And there's also using the calculator, and I'll kind of show you through that. I've got some screenshots of my calculator so you can see the right menus and buttons to press. When a population is normally distributed, we can use an event's z-score and the standard normal curve to calculate the probability of such an event happening. So remember that that standard normal curve has an area of 1, okay? And we have different, based on the z-score, we can see what the probability of being that value or lower or that value or higher is going to be using some math. It's actually some calculus is where it comes from. But we have handy dandy tables that do the calculus for us because we're in stats, not calculus. Calculus is great, but I like stats better. And or we could use our calculator, which again does the calculus for us, and we'll go over both of those. So let's look at this one. I may or may not have been putting together these slides while I was watching TV with my kids. So Frozen and the Lego movie seem to be pretty popular around here. It says the weight of a standard Lego figure is normally distributed with a mean weight of 2.98 grams and a standard deviation of 0.08 grams. What is the probability that we randomly select a Lego figurine that weighs less than 2.92 grams. So we're looking for the probability that the Lego man or woman or figure or whatever is 2.92 or less. So the first way we could go about doing that is to calculate its z-score. So y'all take a minute and calculate the z-score for this Lego figurine here. Same formula we did on the last slide with Christoph and Sven. Also, if you need me to go back over something, or if you need me to slow down, re-explain something, use the ask a question down in the bottom right corner. I'll be glad to explain something also on that. Okay. So we have negative 0.75 for our z-score. Does anybody, can y'all confirm that? A few people confirm that value? I do have my calculator here. I guess I could confirm it. Oh, I trust Josie just fine. I just, two people have it. That's a little bit better of a, confirm it, I guess. Okay. I actually got it wrong. I typed the wrong thing into my calculator as I did it. So. Yes, I do agree. So it is. So whenever we subtract observed minus expected, we get negative 0.06, and we divide that by 0.08. That gives us negative 0.75. And then we're going to use the z-score table to find the probability. And give me just a second. I'll post that link for you guys in the chat. Actually, I want to do it different. Let's see. It doesn't like AP stats. It wants me to say statistics. Here we are. It is in the formula sheet packet that you guys usually are given for the test that you can print out and refer to. Okay. So, see, I think I can share my screen a little bit differently, and we'll go through it together. Chrome tab. Okay. So if we scroll down, these are all the formulas. A lot of these are going to be come in handy. And then we have our z-score charts. Let me zoom in a little bit for you guys. Okay. All right. And we said it was negative 0.75. So negative 0.7, 7.1, 7.2, 7.3, 7.4, and 7.5. So the probability of having a z-score of negative 0.75 or lower, because you can see it here, the way they shade, they always shade to the left. A lot of calculators will calculate that point and to the left. Okay, so negative 0.75 is 0.2266. That is the value on the table that you're looking for. So take your z-score, scroll down for your first digit, and then scroll across for your 100th digit. So 0.2266, that's the one that we're after. Okay. Any questions on how to use that chart if that's the route that you Yes, you can, Allison. We are going to look at that on the next slide. I'm just showing you two different ways of doing it. I know a lot of teachers want you to use the charts, and a lot of teachers want you to use the calculator. And we'll go through the way that you're talking about with the calculator. Find the area under the normal curve of the Lego weights with the mean of 2.98 or whatever it was. Okay, so let me swap back over to my slides real quick, and then we'll keep on keeping on. I just wanted to show you all that chart because I know a lot of teachers, that's the route that they go. And I prefer the other. Okay. I prefer the calculator as well. So I'm not British. Okay, so then I kind of took a little screenshot here. -0.75, 0.2266. Okay. And then using the calculator, same problem. All right. So if you're writing it out to show your work, you're going to go into your calculator and select NormalCDF, and you have a lower limit, an upper limit, a mean, and a standard deviation. Those are the 4 parameters that you want to enter into your calculator. Now, if you're showing work on the AP test, you want to make sure that you label your calculator speak. Anytime you use one of the calculator functions, such as this, NormalCDF, okay, CDF stands for cumulative density function. So you're adding up the accumulation of a density curve, okay? PDF is point density function. You're finding the area at one particular point, which we don't really use for normal curve. It does show up on like binomial and geometric, which is another topic we'll get to in a few weeks, I think, via the cram pass. So the low limit in this case is like negative infinity. So I just put negative 100,000, negative 1 million. As long as it's 3 standard deviations away from the mean, AP will generally accept those lower and upper limits. And our upper limit is 2.92. Our mean was 2.98, and our standard deviation was 0.08. So we're basically looking, what's the probability of it occurring between these 2 points, the weight of our Lego figure, if this is our mean and this is our standard deviation. And notice it's the exact same. So if you use the calculator to do this, that's fine. I would suggest drawing out a curve and labeling the point that you have, kind of like we saw on the formula sheet, that curve up at the top. I would suggest drawing that out, labeling your mean, labeling a few standard deviations, and label the point that you want, and then shading the correct direction. And then you can write down your NormalCDF. I think you've covered your bases in terms of knowing the parameters and everything like that. Okay, so here's kind of what you're going to select in the calculator. So I went to second and then distribution. This is on a TI-84. It's a little bit different on the TI Inspire. If you have that, I don't have one of those, so I don't really know exactly, but I know it's pretty easy, very user-friendly. So my lower limit was negative 1 million. My upper limit was 2.92. That was the point of my Lego figurine. The mean was 2.98 and 0.08. And I hit enter. It gave me this on the regular calculating screen. And then I pressed enter to it actually to calculate, and it gave me the same answer as the z-score table. Okay. I'm going to put a quick poll out here just because I'm kind of interested. Calculator or tables? How do y'all generally go about those? Calculator. For a normal distribution, yes, you normally would if it is not given to you. If you're doing a sampling distribution or some sort of inference, then you would have to check the condition. In this one, it says that the weight of Lego figurines is normally distributed. So we don't have to, because our sample size was 1. We only had 1 Lego figurine. This was a probability of 1, so like a sample size of 1. But it tells us that our population of all Lego figurines is normally distributed. Okay, that's a good question there. Hopefully that answers. We will talk about the condition that you generally have to check moving forward in just a second. All right, looks like everybody seems to agree with calculator there. I don't blame you. It's a little bit easier in terms of what you're trying to do. Okay, so next is where those conditions come into play. So the normal curve for a sampling distribution. And sometimes we'll have data that's not normally distributed, but when we take that sampling distribution, it does become normally distributed. Okay. In the case of the Lego figurines, we knew that it was already normally distributed. So we already have that normal curve. But sometimes we have data that's not. But if we take a sample of data and take the mean of all of those numbers and looked at taking all possible samples of that size, that's going to be normally distributed. And that's where this comes into play. All right, so we have two types of data. We have proportions and means. So when we're given proportions, that's also known as categorical data. When we're given means, that's also known as quantitative data. Those are the two types of data you're going to be dealing with on the AP Stats exam. One of those two. And it really determines a lot of things in terms of how you're going to approach the problem. So a sampling distribution for proportions, this is the condition that you're going to check to make sure that your sampling distribution is going to be normal. Okay. You're going to make sure that the number of successes, n times p, that's the proportion of whatever's going on, and n is the sample size, is greater than or equal to 10. And also the number of failures is greater than or equal to 10. Okay. The mean of our sampling distribution is always the proportion of our population. That's our p-value. That's going to be the center of our normal curve. And the standard deviation is found by multiplying p times 1 minus p. So the success probability, the failure probability. Divide that by the sample size and then take the square root. All right. And I have a formula that'll pop up in a minute that shows these things a little bit better. For means, can anybody tell me what that is in the chat? What is n greater than or equal to 30? It's kind of a big idea in stats. 3 words. Central Limit Theorem. Yes. The large counts is this one, the NP greater than or equal to 10. So we use large counts for proportion. We use Central Limit Theorem for means. And they're essentially really the same thing, just for two types of data. The mean of the sampling distribution is the mean of our population. The standard deviation is the standard deviation that we're given divided by the square root of n. So when we're finding the probability of something happening and we're dealing with quantitative data, if it's a sampling distribution, you're going to change your standard deviation. Your mean really doesn't change. So you can type it in your calculator the exact same way as you would have the Lego figurines, which I think we might do another example of that in just a second. Okay, and here's your two formulas. You can see it a little bit better there. So for proportions, here's your center. So that's what you're going to put in the mean section on your NormalCDF on your calculator. For standard deviation, here's your formula. Okay, take the given proportion, multiply it by its complement, divide by the sample size, and then take the square root. Really, for sampling distributions, that's really all you're calculating. For means, you take the mean you're given. That's your mean. You don't change that the way you put in your calculator as we did before. And then for your standard deviation, you take the standard deviation you're given and divide it by the square root of n. So notice the square root is only in the denominator on this one. It's over the whole thing on this one. Before we go on, I just want to stress this on what a sampling distribution is, because it's something that it took me a little bit to get used to and really figure out what it means. A sampling distribution for, let's say we're talking about the Legos and we're drawing out 30 Legos, which might be the question we're going to do on the next slide. The sampling distribution is going to be the average weight of 30 Legos if we took every single possible sample of 30. That is the true sampling distribution. We take all possible samples of whatever the sample size is, and we average each of those together, and then we take those averages and average those. So the sampling distribution, the normal curve that you see, is every data point, okay, is one of the possible samples of size n, whatever it may be, 30 in that case, the one I presented. Okay, so if you take all those possible samples and you make that your data set, every single possible sample, that is your sampling distribution. Okay, So you're taking the average of all of your p-hats. If you're taking proportion, I asked a whole bunch of people a yes or no question, and then I take just a sample of 30. Okay, then if I, out of my whole population, if I took all possible samples of 30 and took the average proportion that said yes and put those into a distribution, that would be your sampling distribution. It really is very necessary in the fact to understand that it is all possible samples of that size n. And then we can see with inference of, oh, well, of all possible samples, here's my middle and here's my standard deviation. The one sample I have is way off the charts. So something's not right. And I know my sample was right and it was randomly selected. Then it must have been the claim that they made about the center. It must be centered at something different. And that's where the inference comes into play. So calculating probabilities with sampling distributions. So same problem. Lego figurine normally distributed with a mean weight of 2.98, standard deviation of 0.08. What is the probability that we randomly select a sample of 15 Legos with a mean weight of 2.92? Okay. Does anybody have any comments about the question here? Anything you want to point out before we actually calculate it? Does anybody see anything here that you're like, oh, that doesn't really make sense? What does our sample size have to be in order for us to use the normal curve? Everybody says 30, right? Because we are dealing with means here, clearly, means and quantitative data. Now, do we have a sample size of 30 on this problem? No. But can we use the normal curve? Do you think we can still use the normal curve even though our sample size is not 30? Nope, Riley, you skipped the one step between drawing out a box plot. So we always check first if our sample size is large enough. And if not, we can look, if it's given that our population is normally distributed, like it is here, then our sampling distribution is normally distributed, okay? So if our population is all Lego figurines is normally distributed, then our sampling distribution of whatever size is going to be normally distributed. That kind of goes back to the question asked earlier about conditions, okay? This one way of checking the condition of normality with a sampling distribution, which ties into the inference we'll get to later, is that if the population is normally distributed, it doesn't really matter what the sample size is. Okay, so that's kind of the way that's why this problem does allow us to proceed in the way that we're about to, because it's given that the population is. And then if it's not given that the population is, and it's not given that the sample size is large enough, we're going to do what Riley said and draw a box plot of our data and make sure that it's not strongly skewed and there's no apparent outliers. And then we can sort of use a normal distribution to continue our test. So we need to calculate our mean, which is 2.98. That was the given mean of our population. That's the mean of our sampling distribution. All right, our standard deviation, here's the way we would calculate that. 0.08, the standard deviation that's given, divided by the square root of the sample size, 15. Okay. Something else to note there with sampling distributions, this comes up in our conditions as well. We have to, in order to calculate our standard deviation, we have to have, our sample has to be independently selected. So since our population of all Lego figurines is going to be more than 150, we can assume that it's independently selected. So even with sampling distributions, those conditions still come into play. We had randomly selected as well, we could make note of. Okay, random, normal, independent. It's reasonable to believe that our population is more than 150. Okay. So then our probability. All right. Normal CDF again. Notice that from the last problem, only one thing changed. What's the only thing that changed with our sampling distribution probability as opposed to just our one Lego figurine? Well, the answer changed, but what else changes on there? Feel free to throw that in the chat. What is the one thing that changed from my answer? Okay, my answer is drastically different, but only one of my parameters caused that to change based off of the randomly selecting one Lego and randomly selecting a sample of 15 Legos. What was my difference there? Okay, standard deviation. I think that's Hannah that said that. Standard deviation changed clearly. Okay, it was 0.08 right here. Now it's 0.021, so much smaller, 1/4 of what it was essentially. And that happened because the sample increased. When our sample was 1, we could think about dividing it by the square root of 1, which is 1. Now we're dividing by the square root of 15, which is much larger. Okay, it's pretty close to 4, like I said. So since our standard deviation is smaller, remember that normal curve, it's going to shrink in. As that standard deviation gets smaller, remember that's how spread out our normal curve is. It's going to be shrinking in. Okay, so that standard deviation gets smaller, our curve shrinks in. Now our data point of 2.92 didn't move. Okay, it stayed where it was at, but since the curve shrinks in with it, because that standard deviation getting smaller, that makes the probability much smaller. Okay, and I did make note of that there. So since this one told us that the population was normally distributed, we didn't have to check the central limit theorem. That should be underlined too. Okay. Any questions on sampling distributions? All right, and then calculator picture here. You can kind of see what's going on. Okay, let's look at one with proportions. According to a recent poll, 85% of all Americans vote strictly according to their political party in all major elections. If we take a random sample of 500 people, what is the probability that more than 87% of our sample voters will strictly adhere to their party? Okay. Are we dealing with proportions or are we dealing with means on this problem? Categorical quantitative. Proportions. Yes, we are dealing with proportions. You see the percentage there, that kind of gives you that prompt that it is there. So the first thing we need to do, can we use a normal curve? Okay, 0.85, that's our proportion of our population times 500, which is our sample size. We would expect there to be 425 people that would vote for their party. So that's greater than 10. We would expect 75 people to not vote strictly for their party. So that's greater than 10. So yes, we do have a normal curve. All right. The mean of our normal curve is 0.85. So think about whenever you have a normal curve for proportions, your center is, all of your data is between 0 and 1. Okay. Because you're dealing with a proportion. All your data points are a particular proportion. Okay. So it should be centered at 0.85. Okay, that should be the most likely outcome, the mode of your normal distribution. Your standard deviation, you would do your formula, 85 times 15 divided by 500. That's your sample size. Take the square root, 0.016. Okay. Note that it is reasonable to believe that there are more than 5,000 American voters, so our sample is independent. That independence check ties with the standard deviation. The normal check ties in with the normal CDF. So you see where those checks for inference, those conditions, tie into different parts of the problem. Standard deviation requires independence. Normal check, normal CDF, anything normal, calculating that p-value we're going to get to, ties in with that normality. Okay. And then random, if you don't have a random sample, then you could just ask the people who are going to go against what you're trying to prove. So random sample really is the crux of everything. So our probability, our lower limit is 0.87. Our upper limit is 1 because that's the highest your proportion could be. Okay, this one was more than 87%. That's why we went to the right. So we're looking at a tail on the right here. Your mean is 0.85. Your standard deviation is 0.016. And that gives you a 10.5% probability. There is a 10.5% chance of selecting a sample of 500 voters where the proportion of those who vote strictly by party is 87% or greater. So we're looking at what's the chance that our sample is 87% or greater, not just one voter, but all samples. So this is calculating. Oh, didn't mean to go there. So this right here is calculating. It's looking at all possible samples of 500 and seeing how that would play out. Okay. All right. So then the normal curve and inference. This is where you really start to use the normal curve for some kind of interesting things. So when we want to calculate a probability with the sampling distribution, this is the primary way in which we can check statistical claims and make inferential decisions. You have a null hypothesis and you're trying to see if that's true or not. You can use the normal curve to do that if, in fact, that normal condition is met, which is what was brought up a little bit earlier. So when you have proportions, that's what you need to check in order to use the normal curve. When dealing with means, that, or if the population is normally distributed. So it gives you the ability to use the normal curve to see, number one, how rare is it for a particular sample to occur? Or two, it allows us to calculate an interval that gives us an estimate of where the true proportion or mean is. Okay, confidence interval, significance test. Both of those have to have that value. They are both very dependent on our sample size. The larger our sample size, the more accurate our test is, or the more accurate our interval can be used to predict that true mean or proportion. A really big sample size is going to give us a smaller interval, which really helps us hone in on that true value we want. And then it's also going to make your test more accurate. It's going to make that p-value closer to what the population is. So an example. Carl Fredrickson is seeing how many balloons it's going to take to lift a house. He has read that it takes 450,000 balloons to pick up an average house. So Carl goes around the neighborhood and he tries out 40 houses to see how many balloons it takes to lift them. He performs a t-test because we're dealing with means here. He's talking about the average amount it takes, not a proportion of houses, but the average amount of balloons. Okay. So he does a t-test to test the claim that 450,000 balloons is what it takes on average to lift a house. Why is it important that he tests at least, or why is it important that he tests 40 houses? Couldn't he have just done it with 2 or 3? What about 40 houses is kind of the magical mark there. Okay, it's above sample size. It's a good sample size. Yep. What condition is that relating to? It is relating to the normal condition to reduce sampling variability. That's really good. That's another good way of putting it. Because if you only took a sample of 2, well, what if you took the smallest 2 houses or the largest 2 houses out there? So your sampling variability is off. 40 is greater than 30, Central Limit Theorem. Good. Okay. And I could just see this being a big issue this year. Normally, you're doing the whole test. With this year's test, with the time constraints, and with the not having access to calculators, I could see this being one of the questions. Like, yes, it is the normal check, but why do we need the normal check? Okay, we need the normal check because it is in order to assure that his sampling distribution is normal. Okay, regardless of what the distribution of number of balloons it is to pick up every house. Okay, we don't know that. But we know that the sampling distribution of that, as long as our sample size is more than 30, is going to be normal. Okay, so he's after the sampling distribution to calculate that p-value that he's ultimately going to do. Since his sample is large enough, greater than or equal to 30, like we mentioned in the chat, his sampling distribution is normal, and therefore he can use a normal distribution, which is the t-curve in this aspect, to calculate the probability of achieving his given sample. So I was a little bit more specific in the way I worded that out instead of just saying it's a normal curve. But the sampling distribution of 40 houses is normal. And therefore, his one sample, he can see where that's at. Was it really, really rare that he collected that one sample? Or is his sample kind of right in line with all the other samples? Okay. B, what is a potential problem in Carl's study? This is not really dealing with a normal curve, but I think it's a great question. So can you identify a problem with Carl's study? Besides the fact that he's picking up people's houses randomly, I mean, that's a big enough problem, right? But with the statistics behind it, what's a problem with what Carl is doing? Not random. Yes, good job, Riley and Josie. Okay. How do we know it's not random? What in the problem tells us that it's not random? I know this is annoying for you guys who are used to a regular classroom to type out the answers. He just walks around the neighborhood, right? Okay. He tries out 40 houses, right? So anyways, yeah, so that's the problem. How could he improve the study? Okay, I'm not going to make you guys type all that out. He only sampled houses in his neighborhood. It's not a random sample, and therefore it cannot be generalized to the population of all houses. Perhaps the houses in his neighborhood are smaller, so therefore they are lighter and don't require as many balloons as the average house. He could improve his study. I didn't actually put this in the response, by doing some sort of randomization process and choosing 40 houses at random. But a lot of times we check that random sample and just like check it as a box, but don't really understand why we do that. So I wanted to be really clear on that, just while we have a chance with the way the AP test is looking different this year. So the reason why we do a random sample is that so we can generalize our findings to whatever population we're trying to generalize. Remember, sample is a small picture. That's what we can find. We can do a sample of 40 houses, but we can't do everybody's house. So we want to be able to do our sampling random enough that that smaller sample can be generalized to a much bigger population. Okay, it's called your scope of inference. Your scope of inference is what you can measure and generalizing that to the big picture. Okay, he can't generalize his sample to all houses because he only went in one neighborhood. Okay, it wasn't random. And I also provided a direction that things could go. A lot of times when questions like this, AP will look for that. Perhaps the houses in his neighborhood are smaller. You also could have said bigger. So therefore they are lighter or heavier and don't require more balloons, but implying a direction there is really important and giving a specific example. Okay. Same question. It says he performs a t-test. He straightens out the normal. Okay. He calculates the mean of his sample to be 425,000 balloons and a standard deviation of 2,000. Carl calculates a p-value of approximately 0. Given that he fixes the randomness issue discussed in part B, so he fixes that, discuss in terms of the sampling distribution what this probability of 0 means. So basically what that's saying is that it was essentially impossible to achieve a random sample of 40 houses where the mean number is 425 with a standard deviation of 2,000. Okay, that is not at all possible if the true mean is 450,000. Okay, so that's kind of the problem there. In finishing our t-test, of course, he would state that since our p-value is low, we reject the null hypothesis given the article he read. He does have convincing evidence that the true mean number of balloons it takes to lift a house is different than 450,000. Y'all are used to that statement there. But what that p-value represents is the probability of drawing a sample that is the sample that you have. And if that probability of drawing that sample among that sampling distribution is really low, that's where we drop the hope. Okay. So I just wanted to go a little bit more in depth on what that p-value means, tracing it back to the normal curve and the sampling distribution for that particular sample size. Okay. Any comments or questions? try to keep it around 55 minutes, so I'm a little bit over. But I will hang out for a second if you have any questions, and we can hash that out for sure. So type your questions in either the ask a question, or you can just put them in the chat for now, whichever one is better for you. And I will make sure that I can help you guys out. Okay, normal distribution you're going to see it on the AP test in a few weeks. I guarantee you. Somehow you need to see where it starts with just basic probabilities and z-scores and expands all the way into inference, which is probably the most common way you would see it. And don't just expect them to ask you to check the conditions for inference. They're probably going to give you one of the conditions and want you to explain it more, kind of like we did with normal and random there on that last question. Okay, so I kind of try to take a different approach than maybe what we're used to in terms of AP questions to do that. Normally we just see do the data, present convincing evidence that so-and-so is less than so-and-so, and we do our normal either SPDC or phantom, whichever your teacher does, state the hypothesis, do your conditions and all that. And I really expect it to be a little bit different this year with the time constraints and the technology restraints. Okay, no questions? No questions. All right, guys. Y'all have a good week. I will see you guys back here next week. Be sure to check out Fiveable for all of your other classes that you might need. And y'all have a great week. Bye, guys.